Alright, here's sort of a shorter problem, but still an interesting one. So, we've got a CeLO P subgroup of G, and we have its normalizer. And of course, the normalizer of P and G, we're just going to call it N for short. It's just the elements such that GPG inverse is going to be equal to P. And then we prove that for every single subgroup L which is between N and G, so it contains N and is contained in G, well obviously it's contained in G, then the normalizer of that subgroup is precisely the subgroup. Which is kind of interesting because we don't really know anything about P. Well, we know it's a CeLO P subgroup, but we don't know what P it is. But anyways, the CeLO theorems allow us to actually get something out of this problem. So anyways, we know that any group is contained in its normalizer, and so L is contained in NG of L. And that's something that you can really quickly verify on your own. So if you take any element of L, then let's see here. You want to prove that GLG inverse is equal to, so basically what we want is for all L in L, we have L times L inverse is equal to L. And you can just do that by inclusion here. Obviously, if you take an element L times L naught times L inverse, this is going to be contained in L, since you're just multiplying three elements of L together. And then if you take any L naught in L, you want to show that it's of the form L capital. You want to, for any, so for all L naught in capital L, we have, if you take L and then multiply by, well, L inverse L naught L inverse, this is going to be L naught. And of course this thing is in capital L because you're just multiplying together two elements of L. And so anything that's in here is going to be in here. And so we have by inclusion, and therefore any group is contained in its normalizer. Alright, so now that we're done with that tangent, we want to do the other inclusion. Let's erase all of this. So anyways, we're going to suppose that we have an element G in the normalizer of L. And so what do we want? We want to prove that for any element in the normalizer of L is going to be contained. So we have this inclusion and we want the other inclusion. We want this direction. So we want to prove that if you have an element in the normalizer of L, then that element is going to be an element of L. Alright, so we know that P is contained in N is contained in L. And so if we just take this and we, so P is a subgroup of L. And so I guess in this scenario we don't really need this part, at least not in this statement, because what we're using here is that if P is a subgroup of L, then you just multiply on the left by G and the right by G inverse, and you get GPG inverse is contained in GLG inverse. But GLG inverse is equal to L. Actually, the reason that GLG inverse is equal to L is exactly the reason that this equality holds is precisely because G is in the normalizer of L. And that's exactly what it means. And so that's why this equation holds. And so now we know that for any subgroup H of G and for any element G naught in G, this is just a general fact, you have the size of G naught H, G naught inverse is equal to the size of H. And that's because the only way that this could not hold would be if you have like G naught H1, G naught inverse equals G naught H2, G naught inverse, i.e. you take two elements and you multiply on the left by G naught and you multiply on the right by G naught inverse and you get the same element of H. But this is impossible. Well, if this equality holds, then you just cancel on the left by G naught you just cancel the G naughts on the left and you cancel the G naught inverses on the right, and you get H1 equals H2. And so these two sets here have the same size. Right, so therefore, P and conjugating P by G are both going to be CeLO P subgroups of L, because we have both P is contained in L and G PG inverse is contained in L. And so these are both subgroups of L, and we know that P is a CeLO P subgroup of L, and we know that conjugating by G is going to maintain the size, and so conjugating by G is also going to give us a CeLO P subgroup. Anyways, okay, so we have two CeLO P subgroups of L, and by the CeLO theorems, we know that these two CeLO P subgroups of L must be conjugate in L, and this in L here is the key to this problem, because that's what's going to sort of put everything together. We sort of knew already that P and GPG inverse would be conjugate because they're CeLO subgroups, but because they're subgroups of L, we get this conjugation to take place in L. So that means that there is some element L that's contained in capital L such that you conjugate GPG inverse by L, and you're going to get P. And then you just rewrite this thing, and then we've got LG times P times LG inverse equals P. But the normalizer of P is just the set of elements that do exactly that, and so LG is contained in the normalizer. And so what we can do is we can write G as L inverse LG, because L inverse L is just going to be E. But look, obviously L inverse is going to be an L since L is a subgroup, and we just proved that LG is contained in L because LG is contained in the normalizer of P, which is contained in L. So therefore we can write G as a product of two elements of L, which means that's in L, and this holds for every single G in the normalizer of L, and therefore the normalizer of L is contained in L, and that's the other inclusion that we wanted, and hence we have the final equality that we wanted, and this completes the exercise.